Okay. Okay, so welcome everybody to this new IFIMAC+ICMM joint seminar on condensed matter. I am Carmen Munuera from ICMM, and I will be chairing the seminar today, and Pablo San-José, also from ICMM, will be hosting it. So today is my pleasure to present our speaker, Pablo Alonso-González, a distinguished researcher from Oviedo University and the Nanomaterials and Nanotechnology Research Center, who is going to talk about nano-optics with 2D materials. So let me give you a short presentation. And Pablo heads the Quantum Nano-Optics Laboratory in the Physics Department at the University of Oviedo since 2017. And previous to this position, he was a postdoctoral researcher in the nano-optics group from Professor Hillenbrand at CIC NanoGUNE in San Sebastian, and a visiting researcher in the Institute of Physics at the Chinese Academy of Science. So Pablo's research activities are focused on material science and nanophotonics, with a special emphasis on the study of optoelectronic properties on novel 2D materials at the nanoscale. He's a worldwide expert on the study of light and his interaction with matter at the nanoscale. And among his major achievements, we can highlight the first visualization of guided light in graphene with nanometric precision, and his investigations on directional polariton propagation in anisotropic 2D materials. In 2014, he was awarded the Royal Spanish Society of Physics Reserve BBA Foundation Prize in the New Researchers in Experimental Physics category. And very recently, he was finalist of the European Falling Walls Prize in the Physical Science category, recognizing scientifically groundbreaking discoveries. In 2017, Pablo was awarded with the ERC Starting Grant, and right last year, he was awarded with an ERC Consolidator Grant. So today, Pablo will be talking about these nano-optics experiments. And thank you, Pablo, for accepting the invitation, and the floor is yours.
Okay, thanks, Carmen, for the kind introduction. Okay, so I will go directly to the presentation. The title is Nano-Optics with 2D Materials. It's a kind of visual presentation because we do microscopy, so we can see these effects at the nanoscale. And particularly, I show you here 3 images that are part of the results I'm going to show you in the following. In this first, I don't know if you see my cursor. I hope you can see it, right? Or not? Okay.
I know.
Wait. Now or no? No. Sorry. Okay. Now I think you can see it.
Yes.
Okay. So this is the one of the results that I'm going to show you, which is a kind of a strange propagation of nanolight at the in certain materials, a van der Waals material, molybdenum trioxide, and this is what we call hyperbolic nanolight. And this hyperbolic nanolight has very intriguing properties, which give rise to exotic effects, optical effects, like negative reflection. This is something that I'm going to show you as well. And one effect that is very special and happens when this material is stuck in 2 layers, which is called canalization, and where the polaritons propagate along one specific direction, like in a waveguide will be. So let me start first. This is the outline of the talk. I will try to explain a little bit more about the nanolight in this material, alpha molybdenum trioxide. But before that, let me just give a few slides where I'm going to explain in detail why we are doing nano-optics this way. So you all know that the diffraction limit of light imposes that the spatial resolution is always larger than the wavelength of light divided by 2. And if the wavelength of light is very long, like for example 1 micron, 2 microns, and so on, we can only focus this light to several hundred nanometers. So we cannot go to the nanoscale, right? Well, there is a solution, and the solution is the excitation of surface polaritons. I put here surface plasmas because they were the first ones to be used. And these are surface waves. They are solutions of Maxwell equations. And they have a particular property that makes them very interesting. It is that they combine the character of light, but also the character of the material, and in particular of matter, and in particular free electrons in for example, in a material where the permittivity is negative, and it could be a metal and can be others, as I'm going to show you in the following. So this hybrid character of the surface wave make it very special. This is shown here in this dispersion curve, where this wave, this is the dispersion curve of this wave, of this surface polariton, and this is the dispersion curve of normal light. Okay, and you can see that it lies to the right, meaning that the fixed frequency, for example, omega, the momentum of these surface polaritons lies to the right, and then it's larger than the momentum of the incident light. This meaning momentum is 2 pi divided by lambda, meaning that lambda it's smaller than the incident of the wavelength of the incident light. So we can go it's these surface plasmons or surface polaritons, they work as funnels that permit to confine light to the nanoscale. Okay, the conditions of excitation of these surface waves is that there are these kind of two materials in where they are excited at the boundary between two materials, where one has a dielectric nature and the other has a negative permittivity, as I showed you before. And therefore, these are the properties, right? So the polariton wavelength is much smaller than the incident wavelength, and also you can confine the field at the nanoscale, so the field of the polariton is much larger than the modulus of the field, much larger than the incident field. So this has been, you all know probably all these things, but I wanted to do just a very basic introduction to go later to the more technical things. This has been studied for years in metals, right? And this is because this material with negative permittivity is well fulfilled with metals below the plasma frequency. One can think of it like when one illuminates a metal, the free carriers that are in the metal, because they have a negative permittivity, they try to screen out this incident field. They screen it out by moving these carriers such a way that they create dipoles that cancel the incident field, right? So, okay, this has been studied for years, and there are key results in this field, like single molecule Raman spectroscopy using optical metal nanoantennas, where localized plasmons are excited in very, very small volumes. So you can illuminate only, it's like a nano lantern, where you can illuminate only one molecule, and therefore you can have this signal, right? This Raman signal. But let me say that the plasmons show also some drawbacks. For example, they have strong optical losses. The lifetime of these polaritons of surface plasmons is in the range of 10 femtoseconds. And this is because electron-electron scattering is the physical mechanism that dominates and makes it that the wave decays very fast. And there is also this lack of electrical control. So because you can, just by putting an electric field, this is screened out by the metal itself, and then you cannot control the properties of polaritons in an active way. So, okay, this is a summary of plasmon surface polaritons in metals. But now I want to call your attention to another kind of polaritons, which are phonon polaritons. The physics is the same conditions for Maxwell equations, these surface weights, etc. But in this case, instead of having a negative permittivity because of the free carriers in the metal, we have a negative permittivity in the material because of lattice vibrations. These are phonons. So it is well known that polar crystals, they have this, their permittivity is negative between the TO and LO phonons, and this happens in the infrared spectral range. It's called the Ristral band, and it's because, in the same way than before, when the infrared light comes to the material, because it's a polar crystal and it has one atom is more electronegatively charged than the other, there is a tiny dipole next to these phonons that can react also, screening out the incident field. So instead of having this collective movement of electrons, now we have this collective movement of the lattice that also screen out the incident field. And by screening out this incident field, it creates this surface wave on the material that has the same properties than with surface plasmons, such as strong confinement and so on and so forth. But instead of having such short lifetimes of 10 femtoseconds, in this case, because the main mechanism, loss mechanism in phonons is phonon-phonon scattering, and in this case, the lifetimes are in the picosecond range. The phonon polaritons that are excited, they have this exactly more or less this lifetime, picoseconds. This is key for applications where you want to control light-matter interaction and you want it to be enhanced, right? It has also some drawbacks, particularly when one works on these polar crystals that are bulky, like silicon carbide and quartz, because they are difficult to engineer. Another drawback that is intrinsic to phonon polaritons is that they occur in this crystalline band. It's difficult to extend it, although there are some works that are they have some nice results on extending it. Also, the active tunability is missing in these polaritons. So we gain on lifetimes, but we also have some drawbacks. But in this scenario of results on polaritons, in phonon polaritons, graphene plasmons, and so on, the 2D materials appear to be really helpful. Particularly, we have here kind of different families of 2D materials. Here I put here, well, this is a nice review. Here are the references where they differentiate between, for example, graphene, black phosphorus, semi-metals, where they can support graphene plasmon, plasmon polaritons. And in this case, because they are thin, you can do field effect, and then you can make active tunability of the graphene plasmons. This is the difference with the bulky systems or noble metal systems that worked before. And this was really a great advance in polaritonics or in nano-optics. And now I want to go to this part here, which is the phonon polaritons in 2D materials, like hexagonal boron nitride, and particularly I'm going to show you in molybdenum trioxide. So the same way that I said before, you have these lattice vibrations that they can be coupled to light and giving rise to this surface wave where light can be confined. There are other polaritons that are being studied, very, very interesting, like exciton polaritons. These have been visualized as well and widely studied, and these two have been predicted still to be visualized or demonstrated, like Cooper pair polaritons. Okay, so let me go to then with this brief introduction, basic introduction to this surface phonon polaritons or nanolight in molybdenum trioxide. So molybdenum trioxide is a material that it's really anisotropic. It has an orthorhombic lattice structure. You can see it here with this rhomboedra. The lattice constants along the three directions A, B, C are quite different. And this makes that when it's a van der Waals material, okay, that when one exfoliates this material, you just take and then you peel off some layers from it, they all are like very anisotropic as well, elongated along one direction and shorter on the other. When measuring the optical properties in the far field, this is in the infrared, long infrared range, you can see that it reflects quite a lot in some bands. It reflects because in particular, the epsilon is negative in these bands, right? This is the Ries-Strahlen band. So here we believe at the time that it could support phonon polaritons in these regions. But these polaritons will be expected to be really anisotropic because of this intrinsic anisotropic nature of the material. Therefore, here I go to, so one ingredient is the material, van der Waals material, molybdenum trioxide, but the other ingredient to visualize these phonon polaritons is the system, I mean, the microscope that we are using for this. And this is a scattering near field optical microscopy. It's basically an AFM system where the tip is metallic. It is illuminated with far field light. And by being illuminated, there is a property. Well, you remember that the dispersion of polaritons lie on the right, on the incident light. So if you just inside with free space propagating light, you cannot excite these surface waves. You need extra momentum. You need to beat this momentum mismatch to launch these waves, right? And this is the key why they are also with a smaller wavelength, right? They have a smaller wavelength. So this system, this AFM tip, that is illuminated, allows to provide this high momentum. And how is this? You can see it's like this is a simulation of the electric field of in the metal tip when it is illuminated by electric field like this, and you can see that by this shape of the metal tip and so on, you can see that it is localized here, the field, the electric field in the tip, and when something is very localized, you can see it in a mathematical way. You can do the Fourier the Fourier transform of something that is very localized in space to momentum, and then you can see that we have a broad range of momenta that can be reached by localizing the field here at the tip. So now we have available many cases available here that can beat this momentum mismatch and excite the wave, right? This is the key of SNON to visualize nano-optics and to excite these surface waves and so on. Okay, so we measured here in some frequency where we saw here a peak of the reflection spectra. So we thought that here there were some phonon primes to be excited, and then we saw this. They are more or less, they look like isotropic because the wavelength is same here than here. These fringes are the polaritons propagating. And then we measure here in this other band where the reflection was large. And here we saw this striking image where there were no fringes in this direction, but there were only fringes in this other direction. So this indicated that in the plane, because we are looking here at the polaritons in the plane in this material, there are some frequencies where they are highly anisotropic. They propagate on certain directions only. So, but what directions are they propagating to? To measure this, we thought, okay, we need to probe all directions in the material. And to do that, we decided to make like a disk in the metal. We did this by focus ion beam. Then we use the tip to excite the polaritons. The polaritons propagate in the material, and they can, I mean, they are, I didn't explain this, but the SNON tip works like an echo detector. So it launches the polaritons in one position, but it measures also at that position. So it measures what is coming back. It's like a radar. So if you want to probe all directions in the material, you can make a disk, and then you put your tip here. For example, it launches, they go to the edge and then come back, but they go to all edges, right? They go to all directions in the disk, and then you can see if they propagate in all of them. And for the first frequencies where we saw this kind of isotropic propagation, we saw this this pattern. It's an elliptical pattern. And in the other frequency, we saw this kind of almond-shaped pattern, where there are fringes coming back to the tip when they are launched, almost at all directions, but not, for example, at this direction. To see better this kind of propagation, we can do the Fourier transform of this real space image. And then you see these plots here that are called isofrequency curves. Isofrequency because they're giving at this fixed frequency, and it's in momentum space, right? So this is kx, ky. And this is all the directions that are available for propagating on polaritons. Here they are elliptical. And in this other case, because of this strange real space shape, when one does the Fourier transform, you can find here a hyperbola. So this is what is called hyperbolic propagation of polaritons, and these are hyperbolic phonon polaritons. It's quite peculiar, right? There are some directions where they cannot propagate, some others where they can propagate, but in these others where they can propagate, they propagate with different k modulo of k, right? They have different sizes, vectors here, and all along all these directions. And particularly at the asymptote, you can have infinite number of k's. And this is like an infinite number of optical states. For doing a light matter interaction, this is very important because you have many available k's where the matter can absorb the light and so on. Okay, so, well, another properties of these phonon polaritons in molybdenum trioxide at the time was that the lifetime was extremely large. We could find polaritons that were even with a lifetime of 20 picoseconds, but typically they have like 8 picoseconds in the elliptical regime, and there was a record high at the moment, and I think still it's a record high for any polariton or highly confined polariton. The thing is that we don't see many fringes. You can only see like even if the lifetime is so long, you see like 4, 5, 6 fringes, so six wavelengths propagating until it decays. It's an exponential decay, right? This is because the group velocity of this wave is really small. It can be like 1,000 of c. So this is a trade-off. I mean, if you want something that is really confined, it will propagate slow, and the other way around. Well, for applications where we want to look to use this nanolight, where you need long propagating distance, it's not really good. But on the other hand, if you have a cavity, it lives very long in the cavity. It does not need to propagate very long there. It can go back and forth several times, and then you have a high quality factor for a cavity. Okay, so let me come back to this property of the case. You have infinite number of Ks here along this asymptote, but also there is another property, which is that by definition, the Poynting vector of the wave is normal to the isofrequency curve. So typically in isotropic media, you have a circle here, and K and S are collinear. So the wavefronts, right, they are plane waves, and the energy goes exactly along the normal of the wavefronts. But in this case, it is different. Here we have some wavefronts that are like tilted because they are normal to this K vector, but the energy goes in another direction. And this is what I show you here. So the energy goes in this direction, but you can see here, if you take the normal to the wavefronts, that K goes in another direction. So it's really peculiar, this propagation in this material. What I'm going to show you now is that this non-collinearity between S and K yields exotic optical phenomena like negative reflection. And this is how I go to the next result, negative reflection. But let me take you back to the college and explain you a little bit or remind you a little bit about the specular reflection, and particularly when we have a specular reflection as a momentum. I'm looking at a specular relation as a momentum conservation principle, right? Through the momentum conservation principle. So one can see that when you have a boundary, it is indicated here by this orange line, you come up to it with a wave that is this one here, green one. This is the Poynting vector, and this is the K vector. You can see that momentum conservation at the boundary, which is this vector, this blue vector here, it's fulfilled for another K vector here in the circle, which is this one, and this gives rise to this another Poynting vector. So these two vectors explain the specular reflection through the momentum conservation principle, right? And this is because you have a circle, and then you have to fulfill this momentum conservation at the boundary. So what happens if you have a hyperbolic medium instead of an isotropic medium? Well, now we have a hyperbola instead of a circle, and then we can take, for example, this vector coming here to the boundary, like this one. So it comes in this direction. And now, by momentum conservation, the other vector that crosses the hyperbola and has this projection, it's this one. But now the Poynting vector is pointing along this direction. So it is not like before, where you have this one that is collinear to K. Now they are non-collinear, and this gives rise to this other vector that if you put here in the real space, it will give what we call negative reflection, because the wave that is outgoing from the boundary, it's on the same side of the normal to the boundary. So it's like if you look at the mirror yourself in this hyperbolic wall, and then you need to really tilt the mirror to see yourself, right? Well, this is in case if you have back reflection, but it goes in this other direction. Well, we have this material where we have this combination of this non-collinearity between K and S, because we wanted to measure this negative reflection. But I told you that the SNOM works as a radar, right? As an echo detector. So it sees what is coming back to it, right? so so you can see it as a back reflector sensor. So this is exactly how we see each other at the mirror, right? And when you look at this mirror in our isotropic wall, you can see it yourself when you put the mirror perpendicular, right? But, and this is the condition, you have this wave, it goes to the boundary, and the other vector that fulfills this momentum conservation, which here is just the point, is this one. But now in a hyperbolic wall, you have the same condition, this one, it goes to the boundary this way, but the same projection, it goes to this negative back reflection. Okay, it's the same thing, and this is what we could see in SNOM. In SNOM, we cannot have a photograph of this case because we have the tip here, it launches the wave, it goes to the boundary, and we only want to see what is coming back to the tip. If it goes here, we cannot see it. So therefore, I introduce here the back reflection, okay? So we are going to do this experiment of back reflection. We expect to see this thing. In isotopic case, we will expect this thing, and in hyperbolic case, we will expect this thing. So we did the experiment, and we started with a material that is isotropic in the plane, and we did this kind of shapes like mirrors, where you can put the tip, the waves go to the mirror, and it comes back, and then you can see that all the waves here, they go back and forth, K and S, they go collinear, right? As it is expected for isotropic medium. But what happens if we have now a hyperbolic medium? Well, this is the result. So we have the same mirror, and now instead of having this energy going in this direction, we have K going in that direction, but S, you can see here the energy, because the fringes go in that direction, is going here. And this is exactly what we expected from this sketch that I did before. So the back reflection from this mirror is like this. And this is for nanolight and the nanoscale. So here is the simulation. We have a tip. It launches these hyperbolic waves, and then they hit the mirror and they come back to the same position. And we know that they come back because of these interference fringes of going back and forth fringes. So this is the visualization of this negative reflection effect. We could change the angle of the mirror, and then what we see is that the S vector and the K vector, they are changing. You have a certain tunability of the angle of reflection. But here you need to be careful, because you need to, on one side, to see what is S doing and what is K doing. They are not in the same direction. This is all indicated here in this hyperbola. It's a bit technical, but so the message is just that by this hyperbolic reflection, you can control not only the direction where the energy goes, but you can also control the wavelength of the reflected wave. So you can change its wavelength just by reflection, which does not happen in a isotropic medium, right? Okay, so the next step on this negative reflection was to think about what is we want to make a cavity. I told you before that hyperbolic waves, they can have an infinite number or a very large number of Ks along one direction, which is the asymptote of the hyperbola. And this is very good for light matter interactions, but we need a cavity to put some matter in it and then try to couple to this nanolight. To do that, we need to learn what is the cavity shape. I mean, in a isotropic way, if you make a circle and then you have cylindrical waves, you can have a cavity where all of them come back to the origin, right? To the origin of the circle. But in this case, we have hyperbolic waves, and we don't know how they are coming back because the reflection is not back reflection in all cases. It depends on the direction. So we thought, okay, what is the curve at which all these surface waves here? Look here. This is the hyperbolic propagation, right? Here, K and S are collinear, is the only case, but here S goes in this direction and K is like this, perpendicular, and you have all different combinations in all these angles. So you need the shape of a boundary where by momentum conservation of all these Ks that are rotating, they all make back reflection and they all come back to the origin. And this is, in the end, it's really an easy calculation. It's a hyperbola, it's the equation of a hyperbola. We fabricated it, or well, we simulated it first. It has this shape for this wavelength, And this is this is a numerical simulation. And then here we have the dipole that launches all the waves, all the hyperbolic waves. And here you can see that as a difference to here, where there are surface polaritons that leave the reflection at the boundary, they outgo and at very different directions. Now they all come back to the same point. So we have a retroreflector. So all the waves that come back in this hyperbolic wall to this shape, they come back to the origin. Okay, how can we make a cavity? By putting two of them on the two sides. And then this is the simulations as well for the intensity and for this is the field, sorry, and for the real part of the field. And then you can see that this light, this nanolight, hyperbolic nanolight, excited in this material, they go to these reflectors and they come back to it. And we calculated the intensity enhancement at the center. It was 65%, but this was for a very large cavities, like 4 microns, because we wanted to see this effect in this simulation. So you can reduce this size to really small volumes. Actually, you can make it infinitely small volume because you have really, really large case along this direction, because it's the asymptote of the hyperbola. So you can confine light really at tiny spots. Okay. So with this, I want to pass to the, I think I have like 10 minutes to the last part of the talk, and I want to talk to you here about what we call topological polaritons. And these topological polaritons allow us to tune the propagation along previously forbidden directions, or to see or to visualize the effect of canalization that I showed you in the first slide, where the nanolight was wave guided along one specific direction. And this is what I show you here. Okay, what are these topological polaritons? First, let me tell you that these polaritons that I show you in molybdenum trioxide is a biaxial material. It's super anisotropic. We saw that in the literature there was no theory paper where it was treated in a proper way. So we had to do this analysis because of these ordinary and extraordinary waves that happen in the biaxial media. One faces really difficulties in the analytical study, but we were able to do some assumptions and finally get this kind of a compact equation that gives a rise to, that explains the propagation of polarities in biaxial media. Here there are some terms, which is epsilon1 and epsilon3, which are the permittivities of the substrate and substrate. So it's where the biaxial slab is embedded. There is also the thickness. We saw by studying this equation that there are two conditions that are special. When the real part of this permittivity of the substrate and the substrate, the sum of them, it's larger than 0, then we have the typical propagation of polaritons in these hyperbolic waves along the, well, one particular direction of the material is the 1, 0, 0 direction. But if we make a combination of, if we put the slab on a substrate such a way that the real part of epsilon1 plus real part of epsilon3, substrate and substrate, is negative, then the propagation of these polaritons, hyperbolic polaritons, was really rotated 90 degrees. So it could propagate along these directions where before they couldn't propagate, they were forbidden for the material because the material actually was dielectric. It was not, it has no negative permittivity to support these polaritons. Now, when you put it in combination of some substrate that fulfills this condition, then now you have a rotation and then you have propagation along that direction. And this is a representation of the hyperbolic isofrequency curve. Well, these are details of the calculations. If it's a molybdenum tricycle on silicon dioxide, typical substrate in nano-optics, then you have these hyperbolic waves, or hyperbolic propagation, sorry, along this this particular direction, the 1, 0, 0. This is the mode that is allowed in this material. And here, 0, 0, 1 direction, which is the perpendicular, this one, there are no dispersion of polaritons. They are not allowed. But now, if we put it on silicon carbide, which fulfills this condition, we saw that suddenly, where we have here before we had all the dispersion in the 1, 0, 0, this L equal to 0 mode. Now our equation says that there will be a mode L equal to 0 along the 0, 0, 1 direction, the perpendicular direction. And actually we did the hyperbola, the isofrequency curve, sorry, and then we can show here how it is a hyperbola on this direction. The gray curves here are also analytical solutions, but that are overdamp solutions. They are not propagating solutions. So, okay, but I said, well, we did the same experiment. We used a SNON tip as well. And then we tried to visualize how were the propagation of these polarities in MO3, but when it was on top of this particular substrate, silicon carbide, and compared to the case of silicon dioxide, and where we saw here in silicon dioxide the typical propagation along the 1, 0, 0 direction. When we put it on silicon carbide, we saw propagation that before was impossible along this other direction. So experimentally, we prove this prediction of our equation. Interestingly, we track the transition between the propagation along the 1, 0, 0 direction that is indicated here to the propagation along the 0, 0, 1 direction. And we saw it was this striking near field images where we have these cones. And when we did the analysis, theoretical analysis, we saw the L equal to 0 mode, that was the one that was transiting from the 1, 0, 0 direction to the 0, 0, 1 direction. It is closing to the center. It closes here, and then it opens again, but it opens rotated. So you can see here that it's rotated to this side, and here it was like this. So it goes from one side, it closes in 0, and then it opens in the other direction, 90 degrees. And this is what is called an optical topological transitions, because the topology of this curve, this open curve, is different than this one that is crossing at one point. We saw that always that there are this kind of transition, this topological transition, optical topological transitions, there are exotic optical phenomena occurring. In this case, is this reorientation and this propagation along a forbidden direction. And now, in the next few minutes, I want to explain you another one that will give you to this wave guiding. Okay, but this is the first case of topological polaritons. The gap was open along this 1, 0, 0 direction, then it is a gapless curve, and then it's open along the other direction. Okay. Well, this is the 3D plot of this transition. It is open one direction, this one, and then it open in this one, but in the middle it crosses. So, and now it's just the last part where I'm going to show you the second example of topological polaritons giving rise to this exotic optical properties. And this is using or borrowing the concept of the twist slabs in twistronics. Of course, the physics here is completely different. When you have a graphene and then you rotate the graphene, you know that there are these super nice experiments where they can see superconductivity, flat bands at the Magic angle, and so on, right, between the two graphene layers. But we were wondering what will happen, and this is more physics, electronic bands, and so on and so forth. But what will happen if we now take these two slabs of this material, MO3, and then we rotate one to each other? Now, we can think of polaritons, okay, surface waves, electromagnetic, classical electromagnetic waves that can hybridize with other surface waves in the material that is below, and by this hybridization, maybe new kind of propagation types were to be observed. This was the hypothesis, the initial hypothesis, to do this kind of twist optics that we thought. Then we just fabricated the samples. It was quite easy just to take one flake and then rotate the other. In this case, we don't need this kind of super small twist angles like in graphene, by air graphene, like 1 degree or so. Here with 30 degrees, we see huge changes in the propagation, as I'm going to show you now. So we did 30 degrees difference between the two layers, and we use an antenna instead of the tip of the SNON in this case to see the propagation. And then here you can see that the propagation is still hyperbolic, but it's kind of slightly tilted. And now you can see here the hyperbola is not symmetric, and now it's slightly tilted because of this, okay? But still it's hyperbolic. If we put the two flakes at 90 degrees, just like this, we observe the following. We observe, like now we have propagation of polarities along all directions. So we're like recovering the isotropic case, okay? We have like kind of a circle, it's more like a square, and we have propagation, yeah, along all directions, okay, like isotropic-like. And interestingly, at 54 degrees, in this case, we observe this case of canalization, what we call canalization. So all the polarities were propagating along one specific direction, only along this direction, like if a waveguide will be. This is because in this case, and you can do the Fourier transform of this image and go to the isofrequency curve, you have also flat bands, but these are optical bands in the isofrequency curves. And so you transit here from a hyperbola, where it's an open curve, to a closed curve, a circle or a square with another topology, through a flat band condition. And this flat band condition is very particular because it gives rise to this kind of directional propagation. Why is that? Because if you take here, this is a K space, okay? If you take here vectors, you have all Ks, right? Hitting this curve, which are the wave vectors that are available. But as I told you before, the pointing vector is perpendicular to the normal, perpendicular to the isofrequency curve. And the perpendicular to these parallel lines is just one direction. So all the energy goes in one direction. This is what we call canalization. But we have all Ks propagating in that direction. So all wavelengths are available to propagate in that direction, but only along that direction. It's kind of a very peculiar effect. And what we saw is that when we study these waves propagating along this direction, we observe, well, we study the decay of these waves, and we observe that they had no geometrical decay. So normally when you have a cylindrical wave, the cylindrical goes in all directions, so they have some geometrical decay, right? It goes to, you lose energy in the 360 degrees, but in this case, as it is only one direction, and this is the proof by just fitting a mathematical equation, we see that there is no geometrical decay. So it goes exactly along one direction. So, well, this is just a recreation that we did with a sketch that we did where we have these two twisted layers and then they go only in one direction, this nanolight. Yeah, it was, we published this at the same time than other groups. There were 4 works, at least 3 works at the same time, and then another one a bit later. So in this effect, this result was Science Breakthrough of the Year, finalist in Physical Science in 2021, and Breakthrough of the Year in 2022, and so on. Because it opened a new field that we believe can allow to control the light at the nanoscale in unprecedented ways. We think that we can control in the direction that we want, and maybe engineer the wavefront, engineer the wavelength, to have all the degrees of freedom necessary to get the nanolight at will at the nanoscale. And this will be part also, as Carmen said in the beginning, I got recently a near-sea conservator grant, which is called Twist Optics, which is to develop this field. And if there are students listening, there will be open positions for postdoctoral researchers and so on and so forth. Yeah, this is the Quantum Nanooptics Lab at the University of Oviedo. Here, of course, all these people did most of the work, particularly Yahua Duan, postdoctoral researcher, that was the guy that started with the twisted work, Aitana, and then the students, Gonzalo with the negative reflection, Ana working on coupling with molecules, Abel, Christian, and Jose working on theory of particularly these systems where we have several layers and coupling between them. And with this, I go to the acknowledgements. I have to acknowledge many people, of course. These are all collaborative works. the theory with Alexei Nikitin. He's in charge of all this analytical development that I saw you in the equation about these biaxial slabs and so on. In CIC NanoGUNE, we did some measurements in the group of Rainer Hillenbrand, also collaborations with Charlie Bao in Monash University, also DTU people, and then of course the funding. Thank you all for your attention, and I'm open for questions.
Thank you, Pablo. Very nice talk. So we are open for questions, and I think if you have questions, you can unmute yourself or raise hands, and we can unmute. And I think I will start because I'm just curious if this reorientation of the hyperbolic curve. Mm-hmm. You show it with a substrate, but can this be done by using different heterostructure, combining different 2D materials?
Yes, we think so. Here we just did it with silicon carbide because it was the obvious choice just to get the silicon carbide substrate, put the flake of MO3 and do the experiment. But yes, it is true. We can, for example, use silicon dioxide substrate, and then we have MO3, and then we put another, for example, substrate where we have a negative permittivity, where this condition of real part of one plus the real part of the other is negative. And then we will have also the rotation of the we expect. I mean, the question says that we have one demonstration that proves it, and we think that it will work also for others. Yes. This is the great thing about van der Waals materials and all this twisting, right? That you have all the palette of materials that you can exfoliate easily, and then you can put one on top of the other and rotate and so on. So it's really amazing what you can do with this.
Yeah.
Mm-hmm. There's a question from Walter Arnold.
Yeah, thank you very much for your interesting presentation. How does the damping, what's the origin of the damping? Is it due to some defects in the propagation path, or does it couple to some modes into the internal of the material?
Yeah, normally this is phonon-phonon scattering, and this is because of anharmonicity effects. So in principle, there are, well, 2 phonon scattering, 3 phonon scattering. Defects are also there, but normally these materials are kind of pure. They don't have many defects. Actually, we can do it even isotopically enriched. It's not the main mechanism of the loss, but it's more like the phonons that are coupled to the light. They also couple between them, and then they scatter between them, and then you lose part of the energy because of this.
So you mean it's some kind of a Kieser mechanism?
Sorry?
Is some kind of a Kieser mechanism, this phonon coupling only in the surface modes or also to the volume modes?
Both. Well, I call surface modes because it's the solution of these modes is for a surface mode, but in reality they propagate on the volume. For both of them it happens. Still, this is an open question, and we are working on this from a theoretical point of view. There are some conditions where these modes are surface in character, so they only propagate on the surface, and there are other conditions where they only propagate in the volume. And we still don't know how to differentiate between the both of them.
Okay,
it's an open question.
Yeah, thank you.
Thanks.
Okay, another question from Paloma Arroyo.
Hi, Pablo.
Hi, Paloma.
Nice talk. So I was wondering about the dispersion relations that you showed. I think it was for this material.
Yes.
You showed here, yes. So the ones in the left, they are asymmetric in K, right? You seem to be showing propagation only in the negative K direction. So the isofrequency contours in the right are symmetric in K, as I think it should be, no? So I don't the ones in the left.
Yeah. Well, this is because of the phase velocity. So didn't show it here, but these materials, well, particularly in this case, they have negative sorry, a positive phase velocity, and they don't have a negative phase velocity. And in other cases, they can have, for example, this case, it's negative, right? It's negative is on the in the left side, and this is because you have a multiplying factor because of the phase velocity.
Would this imply that you have unidirectional mode? As in non-reciprocal?
No, not really.
I don't think you can, right? So
not really. It's not this way. It's just an effect of it's just a term here that you can add with exponential term with a temporal contribution that is because of a negative. I mean, it's like so yeah, the wave is propagating in both directions, but the phase is only propagating in one case is negative and the other case is positive, but you don't have both. It's a bit, sometimes it's a bit misleading to see the dispersions in wavelength here and to see the isofrequency curves for one specific frequency. Because here you are in K space in the plane, right? K space in the plane, and then here you can see how it can propagate in all directions. Well, not all directions, to the right and to the left. But what you can see here, when we plot this K with negative values and positive values, is just to add here the information about the phase velocity of the wave.
I see.
Yeah.
Okay, thanks.
Okay, I have one question. Hi, my name is Pablo San-José. Thanks a lot. The talk was amazing. So you showed us two instances in which you have a transition between a closed isofrequency curve and an open hyperbolic isofrequency curve. I mean, this twisted optics is one case, and molybdenum trioxide is another case, right?
Yes, yes.
So I have a double question. So in the first case, just without twisting the molybdenum trioxide, what happens if you go to the boundary between hyperbolic and elliptical? Do you have something similar to canalization?
You mean yes. The question is yes. It is not shown here. But if you go and the transition between, because in this case it's a transition between one hyperbola and another hyperbola, right?
Oh, but this is with the encapsulation, right? I'm talking about the first part of the talk in which you were sweeping frequency.
Yeah, this one, right? It's this one. So
this is the one. Okay,
this is the one on MO3 on silicon carbide. So
okay.
Yeah. So in this case, we go from one hyperbola to another hyperbola. Rotated hyperbola, and we pass through some crossing point, right? And in this case, we have this transition. But you are right that if we have the transition between one hyperbola to an ellipse, a closed curve,
yes,
we will have parallel flat bands.
Okay.
And when we have flat bands, we have canalization. And actually, I didn't show it here, but if you go here to less energy, we are working on this now, to lower frequencies, we have the transition from this hyperbola to an ellipse, and then we can have also canalization. And this canalization happens not in a twisted sample, but in this layer of MO3 on top of a particular substrate.
Okay, great. So this takes me to the second part of the question. So the case of flat bands seem to be really interesting for cavities, because the ideal cavity would then be just two flat mirrors. Is that right?
It's even more exotic. So it could have any kind of boundary, any kind of angle of the boundary could give you energy coming back, because the Poynting vector is fixed, right? The Poynting vector goes in one particular direction, and it does not depend on the angle of the boundary to go back along the same direction.
Okay, so that means that however weird is your mirror or your boundary, all the power that you're putting into the system through the tip gets back to the tip.
Exactly. That's...
Okay. And then what is the role of the distance between the two flat bands, the two iso frequencies? Does that affect?
You mean this distance?
Exactly.
Yeah, this distance here is given by the thickness of the flakes. In principle, if one tunes the thickness of these two flakes, one can make them larger or smaller, meaning that you can have for the collinear case, which is somehow dominating sometimes. For the collinear case, I mean that the K vector goes here and the point vector is collinear, because it's this is dominating somehow in the images. This large case, they exist, but they have a very small wavelength, and then the propagation is small and the contribution is not very large. But here it is a large contribution. So what you will see is that if you increase this, if you open these flat bands, then you will have a smaller wavelength dominating the wave guiding. It will be like these fringes will be much smaller. They also will propagate much less probably. And if you make it then closer together, they will be the other way around. They will be
so for the context of cavities, then that dictates the distance between the two boundaries that would give you the ideal accumulation of energy, right?
Yes, that's true. If you have like a very separated flat bands, you have to make a really small cavity.
I see.
Because you have a very small wavelengths. But if you make, you can make it actually what we were talking now. It's actually it puzzles me that you get into this of the cavities with the flat band condition, because it's really something that one needs to think, right? How to orientate these boundaries and any angle it's possible. And actually you can do you can imagine like I don't know a slight defect in the twisted sample that is kind of isolating this part from the rest. It's a cavity. It's a perfect cavity.
Right.
For this case, exactly this case.
Right.
And this is something that we are working on it.
Fantastic.
Because we think that because of these small cavities, plus that the density of states, optical states, is very large because you have all Ks, then the interaction with matter
is going to be
in such a small volume could be very large.
Very strong.
Yes.
Okay. Thank you. Thank you very much. So there is another question in the text from Victor Marzoa. How could we visualize the hyperbolic retroreflector nanoresonator in real space?
This is something that we tried and we were not good enough yet to see it. So this, I told you that these are simulations. So we think that well, we were trying to fabricate these shapes with focus ion beam, but so far we didn't get the exact shape and optical quality to assert this effect with the SNOM tip. If we have the SNOM tip and we make a scanning with the SNOM tip here like this all around, we will have only back reflected waves here at this point. So even if we have like we will have some signals when we are here, we excite these hyperbolic, they go to this boundary, and probably one of the Ks of all the Ks that are launched by the tip will come back, but the signal will be very weak. Only at this point, all the Ks, all the waves that emanate from the tip will come back to here. So this will dominate the image. So we think that the SNOM, this is just a snapshot, right? This is a simulation snapshot of a dipole here, put here, where everything comes back. But this we cannot do with SNOM. With SNOM, I have here the tip, and then I will have a signal here. But when I'm here, I will have another signal, and so on and so forth. It's kind of a different mechanism. But we believe that if we make a scanning of the tip, we'll have something very similar to this thing. Another possibility to exclude the role of the tip that launches at every position, it will be to have here an antenna, small antenna, or a molecule, for example, which will be able to launch these waves. They will receive all, it will receive all of them, and using not a metal tip, but the dielectric tip, not perturbing tip, which is not launching, it's not metallic, so it has not field enhancement at the tip apex. It's just a probe. It's just picking up the fields and sending it to the far field. It's like it will be like the perfect green function in reality.
Okay. Another question from Diego Martin. Please unmute yourself.
Hello, can you hear me?
Yes.
Yes.
Thank you, Pablo, for your great talk. I had a question about this precise image here, and you were saying that you basically have like almost a perfect cavity except for the losses. And my question is, what is the expected finesse, or how many times the waves from the center can pass through the tips and forth, back and forth?
Yes, I don't have a number. We didn't calculate it, but it will depend.
The size, no?
On the size, yes. So how small you can fabricate these two walls, one close to the other. And this is kind of, well, for the moment we are using focus ion beam to then make them really small, but it's not really good. So what we are thinking now is not really good, because you know that there is gallium implantation and all this stuff with focus ion beam, and the optical properties are really, this has a really detrimental result on the optical properties. But what we can do is, you can imagine the slab, a MO3 slab, that is not engineered, but on the substrate, we engineer the substrate, and we make by, for example, gold, where you can do really nice lithographic processes, where you can make really a small gap. We made it made of gold, and then we put a slab on top. There will be a cavity formed because part will be standing on the gold and part will be freestanding. And this will change completely the dielectric environment and the dispersion of polaritons. This is somehow like making a cavity, not by defining boundaries, etching boundaries, defining physically, but engineering the permittivity by another material, in this case, a metal. And in this case, we think that we can make it very small. And still, the reflection coefficient and the reflection capacity of the cavity at this boundary will be high enough to have a cavity. But yes, it's a matter of size. Make it really small, yes. And what is the quality factor? I don't know. Maybe I will expect. I really don't know. I really don't know.
Maybe the quality factor is not very high, but the finesse, yes, if you can make it very small, the quality, then, okay, it decays fast, but it can bounce many times.
Let's imagine, let's say a number. I will expect the quality factor of between 50 and 100, and a volume mode really small, because it can be like, I don't know, 10 nanometers, 10 cubic nanometers, and then the finesse and so on is.
And maybe just a quick second question: is this material, is hyperbolic materials having sometimes defects that act as a quantum emitter in the optical or terahertz regime?
Well, in this case, it's a dielectric. We try to look, because we have another line on single photon emitters and so on that come from defects, right, into the materials. And these materials, they don't have emitters. And one thing that I have to remember is that these polaritons are happening at infrared wavelengths, right? This is 10 microns wavelength and so on. It's difficult to find quantum emitters of these wavelengths. One that is possible that it will work is intersat band transitions in a quantum well. So what we are thinking is that to use, for example, a 2D material where the intersat band transition, the dipole of the interband transition, can couple to exactly this mode in the cavity. It could be a 2D material, or it could be some 3-5 semiconductor where one can nicely engineer the emission of this intersat band transition. Yeah, it's a very interesting prospect in this direction. Yes, for adding quantum coupling to the cavity. Thank you.
Thank you. I don't see any other questions. So I think we can all thank you, Pablo, for this exciting talk. And I thank you all for your attention, and see you next day.